In this video, we'll introduce one of the main concepts of the course, which is the gradient vector. Recall that previously we've shown that the directional derivative of a function of two variables at a point x0, y0 in the direction of a unit vector u with components a and b can be computed using the first order partial derivatives of the function evaluated at x0, y0, and it can be computed using the following formula: f sub x at x0, y0 times a plus f sub y at x0, y0 times b. And if you look at this formula, you can't help but think of the dot product of two vectors, one being your unit vector u with components a and b, and the other vector having the partial derivatives at that point x0, y0 as components. So this leads us to the definition of the gradient vector. So the definition is the following: the gradient vector of f of xy at the point x0, y0 is the vector which is denoted by this upside down triangle of f at x0, y0. Sometimes it's denoted by grad f of x0, y0, but it is just a vector with two components, the two partial derivatives of f at x0, y, evaluated at x0, y0. Okay, this symbol is called nabla, and with this we have the gradient vector of our function. So it's a vector with some very special and important properties. So it tells you a lot about the function. First of all, so let's just collect these properties. The properties of the gradient vector. Well, the first is exactly what we've just seen, is that the directional derivative of the function in the direction of a unit vector u can be computed via the dot product of the gradient vector and u, the unit vector u. Okay, so that shows you that this gradient vector is a really handy tool in computing directional derivatives. Let's just compute one. So let's just compute the gradient vector of the following function: sine of x plus e to the xy, and let's compute it at the point 0, 1. Okay, so pause the video and compute the gradient vector of f at 0, 1. Okay, I hope you paused it and computed the first order partial derivatives of our function. So f sub x is equal to the cosine of x plus y times e to the x y, which at 0, 1 evaluates to 1 plus 1, giving us 2 for the first component of the gradient vector. Now the partial derivative with respect to y will be, well, the first term does not depend on y, so that differentiates to 0, but the second term does depend on y, and it will differentiate to x times e to the xy, which evaluated at x equals 0, y equals 1 will give us 0 because of this x factor. So the gradient vector of this function at that point is the vector 2, 0, so basically 2i, using the basis vectors ij. Okay, so with that, let me return to these properties of the gradient vector. So since the directional derivative in the direction of the unit vector u is the dot product of u and the gradient vector, we can realize that this directional derivative of the function is going to be maximal when u points in the direction of the gradient vector. So because of the definition of the dot product, which tells us that it's the product of the length of each vector multiplied by the cosine of the angle between them, when that angle is 0, then this cosine factor is going to give you 1. So then it's maximal. The directional derivative d sub u of f is maximal when the direction of u is that of nabla f. So again, let me just repeat that the maximum directional derivative is obtained in the direction of the gradient vector. And moreover, we can also compute what this maximal directional derivative is if u is a unit vector that points in the direction of the gradient vector. Then this dot product is going to be the length of the gradient vector. So d sub u of f is maximal in the direction of the gradient vector, and this maximum is given by the length of the gradient vector. Okay, so this gradient vector really contains lots of information in itself. It gives you the direction of the maximum rate of change, the maximal directional derivative with its direction, and with its magnitude, with its length, it actually gives you the maximum rate of change of the function. Last but not least, we can also show that the gradient vector is always perpendicular to the level curves of the function. So let me just say that the gradient of f is perpendicular to the level curves of f. Okay, and we can show this by recalling that a level curve means that we are considering values of the function being fixed at some number k, and if we are along a level curve, so x and y can be parameterized by some parameter t. This vector is a function of t, which satisfies that f of xt yt is equal to k. So this vector function parameterizes the level curve. Now, if we differentiate this equation with respect to t, the parameter t, of course, on the right-hand side we get 0. On the left-hand side we have f depending on xt and yt. So when we differentiate with respect to t, what we get using the chain rule is that we have the partial derivative of f with respect to x times the derivative of x with respect to t plus the partial derivative of f with respect to y times the derivative of y with respect to t. But if you look carefully, this is nothing but the inner but the dot product, the inner product of the gradient vector and the derivative of this vector function parameterizing the level curve. So this is the tangent vector to the level curve, r prime t, and the gradient vector is orthogonal, perpendicular to that tangent vector, so it's always perpendicular to the level curve itself. Okay, so let me make sure we have this clearly visible. With that, I hope you enjoyed this video, and I'll see you in the next one.